So as I told you already, people wanted to know what kind of fate is awaiting us. And there were three possible curves people knew about. And people tried to measure the expansion of the universe far back in time. And more recently, by comparing them, we want to know on which curve we are on. But it led to a surprise in 1998. When people tried to indeed precisely do this measurement, people have found that the universe is, rather than slowing down, it's getting faster. It's accelerating. And we don't really know the cause of it, but we actually named it what may be accelerating the expansion of the universe, and that is dark energy. So what people have done is literally do what I told you. And by measuring the energy and causing the universe to accelerate, or the other way around, by measuring how the universe is expanding, people wanted to decipher what energy is causing it. The only way we can understand it is that dark energy is filling up the entire universe, sort of like the Higgs boson in a way, but with really contributing to the expansion rate of the universe. And it's everywhere. So the way people actually came up with this observation is by using a very clever trick. So there's an astronomical object called Type 1a supernovae, which is an explosion of a star at the end of its life. And it has to actually come from a binary system, namely that you have two stars rotating around each other, one star actually feeding into the other star by providing material. And once the other star becomes so heavy, then it can't sustain itself anymore. It just gives you a big explosion at the end of the day, and that gives you a big flare of light for like a month or so. And you can measure these Type 1a supernovae even at very, very large distances because they are so bright. One supernova becomes as bright as an entire galaxy. And that's great because if you can observe this when it is very far away, you can study the galaxies when they are actually billions of light years away, and that will tell you some information about how quickly they are moving away from us, and that tells you how the universe was expanding like billions of years ago, right? So that way we can measure the expansion rate far away from us. In addition, there's one added bonus with Type 1a supernovae. We pretty much know how bright they are. So if you see one of these things, they're like, okay, you know, it's a 100-watt light bulb. So if this 100-watt light bulb, if that looks bright to you, that means it's close to you. If that looks very dark or dim, then it's far away from you. Just by measuring its brightness, you can tell how far away this light bulb is. And same thing with a Type 1a supernova. So depending on how bright it looks, you can measure how far away it is. And that, in the case of the universe, of course, translates to how far back in time it has exploded. So that's a very good feature of Type 1a supernova. On the other hand, if you measure its color, as we talked about before, that color has reddened because it had been expanded and stretched by the expansion of the universe itself. That's a rubber sheet of the grid we talked about on the first lecture. So by measuring the color or spectrum, to be more precise, you can measure how much universe has expanded since the time of the supernova explosion. So you have an information about time, you have an information about expansion. Putting that together, you have an information on expansion history, and that's how people figured that expansion of the universe is actually getting faster, which is a huge surprise to all of us. So here's the 100-watt light bulb. And that gave us this following piece of data. Namely, the universe would accelerate on this side of the plot and decelerate on that side of the plot. What we used to think is that the universe has only matter, that's 100%, and no dark energy in this direction. And that kind of universe, as we talked about before, should slow down the expansion of the universe, and that's indeed in this decelerating part of the plot. But the data showed that you're up here. You do have matter, which is mostly dark matter, like 25% of the universe, but that can't explain the accelerating expansion on its own if you're down here. You need to have this 75% of the universe in this dark energy so that universe can accelerate. So you can see that entire universe is basically given in terms of the battle between two titans. one titan being the dark matter, the other titan being dark energy, and that competition seems to tell us how the universe has evolved and what is going to happen also in the future. And this measurement gave you this incredible, interesting plot. This shows how the universe has been expanding since, called Hubble diagram. And by fitting this data, you can tell the amount of dark energy we need in the universe versus the amount of dark matter we need in the universe. And this was actually a very clever idea by measuring the supernovae on demand. The supernova, you never know where and when it won't happen. But keep covering a pretty large portion of the sky, at least there's a very good chance that's spotting one. And then you build a system that once you spot one, then you follow that up with other telescopes to measure its spectrum and brightness very precisely. And that's indeed what has been done by my colleagues Saul Perlmutter in Berkeley and other group as well. And by measuring how quickly the supernova fades, in that time scale would tell you exactly how bright the bright supernova was, and that is based on some empirical data by studying the nearby supernovae. People worried a lot about other impacts of the environment, like metallicity, dust extinction, and so on, but they have been shown to be rather less important. It's important at some level, but not that important to change the conclusion that the universe is actually speeding up. And this is the latest data, compilation of data, which had been shown at a conference. So the expansion is getting faster. So what is wrong with this original idea by Einstein? It told us that the universe should slow down, but now we know it's actually speeding up. And this started to happen actually rather recently. Towards the beginning of the universe, it was indeed slowing down, and there are data that shows that. But it started to speed up recently as 7 billion years ago. So what does it mean? So if you think of ball thrusted upwards, it was slowing down for a while, but at some point, it started to pick up the speed and zoom. It just keeps going farther and farther away. So somehow, energy is increasing. Ball is picking up speed, picking up more energy. We don't know what this energy is. That's why we call this dark energy. It seems to be almost as if it's an infinite source of energy, and became a huge impact on general science discussions. Some people even doubted, well, if we get this kind of weird conclusion, maybe it was wrong that we trusted this guy, Einstein. That's why we led to this very, very bizarre conclusion. Maybe he was wrong. Well, a lot of people tried to change Einstein's theory to accommodate this expansion, the accelerated expansion of the universe. Well, we all know Einstein was a pretty smart guy. Nobody really managed to go beyond him so far. So this is pretty unlikely, but people are still studying that. But either way, this is actually incredibly interesting. Either we found a new paradigm of the universe based on dark energy and accelerated expansion, or you find a new fundamental law that goes beyond Einstein. Either way, it's going to be very, very exciting. And also, if this rate of increase in energy is very quick, maybe the universe will keep expanding and speeding up to the extent that the expansion rate may become infinite at some point. Then the universe gets infinitely ripped apart at that stage, and the universe would end there. And this scenario is called Big Rip. The universe is totally ripped apart to infinite size, infinite speed, and there's no universe beyond that point. So what can we do to find out? Well, the only thing we have seen so far is the history of the expansion rate of the universe. And the data are still not accurate enough to tell what kind of fate is awaiting us. So what we need to do is to do a much better measurement with a greater accuracy to measure how quickly dark energy has been increasing, how quickly the universe has been speeding up. So, having heard all these discussions so far, what is the best way to do that?